Section 6.6. So the pronunciation of this section is French. I believe you would say it de Moivre's theorem and nth roots, but that just, do your best on pronouncing that. If you want a fun way of pronouncing it incorrectly, you can call it de Moivre's theorem. That's kind of a fun way, but if you're actually trying for accuracy, it's de Moivre's theorem. So that theorem will come up a little bit later. Right now, though, what we want to talk about is how do we graph complex numbers? Well, complex numbers, if you remember, have a standard form of a plus bi. Okay, and the part here that's a, we call that the real part. And the part here that has the bi, we call that the imaginary part. And so hopefully that makes sense, that the part that doesn't have an I is the real part. The part that has the I is considered the imaginary part. So what we do is we have this thing called the complex plane, which looks just like the regular coordinate system, except that instead of an x and a y axis, we have a real axis and we have an imaginary axis. Okay, so if I want to, on this example, plot the point 1 minus 2i, the 1 is my real part and the negative 2i is my imaginary part. And so I'm basically plotting the point 1 comma negative 2 is how this works out. And so you go on your coordinate system and you go right 1 and down 2, and that is the imaginary number 1 minus 2i. Okay, so you don't like stick the I with it, you just take, okay, this negative 2 is how much I go up or down. Since it's negative, I go down, just like if we were plotting points in the x and the y axis. So with that, we've got a couple green boxes. The first one, we have a definition of absolute value, also known as the modulus of a complex number. And so when you see absolute value signs around a z, which we normally say that a complex number z, for some reason, I don't know. But if you see absolute value bars around z, or you see it around an actual imaginary number, it's asking us to do the Pythagorean theorem basically with a and b. And this should seem really familiar to vectors, that when we talked about the magnitude of a vector and we used absolute value bars, that we ended up doing this right here if it was in component form. It's going to be really similar to that. And what is happening is that in the complex plane, the absolute value, or the modulus of your complex number, is the distance of that point from the origin. So here we have a picture. We've got the real axis and the imaginary axis, and we're just focused on the first quadrant. And so this point, which is a plus bi, has a modulus right here that's the length of this blue line. And so we can call that line, if we want to, we could call that r, and then we would say that this red dotted line, okay, which is the imaginary part of our number, the b right here. Well, couldn't we make this into a right triangle and say that b equals r sine theta? Basically saying the hypotenuse times sine of our angle, this angle here. So isn't that true? We've seen that kind of situation before. And then this part down here along the x-axis would be the real part, which is a. That would equal r cosine theta. So again, this is going to be really similar to what we did with vectors. And this leads us to our next definition, the trigonometric form of a complex number. Okay, so standard form of a complex number is to write it as a plus bi. The trigonometric form of a complex number is you find what r is, which r is simply the distance to your point, which we use by finding the absolute value of our complex number, which is basically like the Pythagorean theorem. That's what r is. And then in parentheses, we put cosine of our angle plus I sine of our angle. And if they give you this to start off with and they want the standard form, well, all you'd have to do is distribute your r and figure out what cosine and sine of that angle actually are. Okay, and it gives us here in this box this definition that that your A equals R cosine theta, your B equals R sine theta. R is the square root of A squared plus B squared, and that the tangent of theta equals B over A. And so the way that we're probably most of the time going to find this angle theta, just like we did with vectors, is going to be to do the inverse tangent of our B over our A. And it also says the number r is the absolute value or modulus of z, and theta is an argument of z. So that's kind of another vocabulary word that we would say theta is the argument of the complex number, but we're not really going to use that word a whole lot, so it's not a big deal. So let's start off by finding the trig form for these two complex numbers. And so I find it very helpful when I start off on these to graph what I have, just like I did with vectors. So I'm graphing 2 plus 2i, so that's going to go right to up to. And we're talking about this point right here. And so we need to find two things. We need to figure out what r equals, and we need to figure out what theta equals. R we're going to get by doing the square root of a squared plus b squared. So 2 squared is 4, 4 plus 4 is 8, so we're talking about the square root of 8, which is also, if I simplify it, 2 square roots of 2. Okay, theta, now we can, if we're looking for this theta here, we can find it by doing the inverse tangent of b over a, but hopefully we are making the connection right now. I went 2 right, 2 up. That should be a 45-degree angle, or we're probably going to want to put that in radians. 45 degrees in radians would be pi over 4. Okay, and so anytime that you end up with something that looks like it could be on the unit circle, that's what you want to use. And so one way to help you with that is if you, like normally we would do inverse tangent and we would put it in radians, but if you did it in degrees and you got something like, 30 degrees, then you would know, hey, that's on the unit circle, and then you could change it to what it is on the unit circle. But anyway, now we just need to fill in basically that formula that was on the previous slide. We have z equals r, which is 2 square roots of 2, times cosine of our angle, which is pi over 4, plus I sine pi over 4. Okay, and that is the trigonometric form of our complex number. You might be asking yourself, why do I care what the trigonometric form is? And we're going to do some stuff with it later on in the section that there are some things that you have to have it in trig form to be able to do it. So let's do 4 minus 7i. Let's graph that. I would go right 4 and down 7, way down here. So that's down here. And so I'm trying to figure out how to draw straight lines on the computer. Try to figure out r and theta. So r is going to be a squared plus b squared underneath my square root. Remember to put that negative in parentheses or to leave it out altogether. 4 squared is 16 and negative 7 squared is 49. 16 plus 49 should give us that r is the square root of 65. To do theta, now if I think about 4 and 7 and the inverse tangent of 7 over 4, hopefully we all are aware that that is not on the unit circle, so I am going to have to use my calculator. So I had to find a calculator. Let's do this in radians, because radians are fun. This is the inverse tangent of 7 over 4. And I know it was negative 7, but I like to leave the negatives out personally, because what it tells me is actually, like when I compute this, I actually am finding this reference angle. I'm totally in degree mode. Hang on, radian. Second tangent 7 over 4. So 1.05 is what that angle is. Okay, but I don't actually want this angle right here. I want the angle to get all the way around. So I want to do 2 pi minus that. So type in 2 pi minus, I can answer. And what I get is that theta is 5.23. Okay, so what I did there was 2 pi minus my answer, which was 1.05. And I got 5.23. Now I'm ready to stick this in to my formula. Z equals the square root of 65 cosine of 5.23 plus I sine 5.23. Okay, and that would be my answer. Okay, this last one says write the complex number in standard form, a plus bi. This is actually really easy. We're just going to basically distribute the 3. And also we'll have to figure out what cosine of 30 and sine of 30 is. Those are on the unit circle. Anytime we have angles that are on the unit circle, we want to use our unit circle and get exact values. So I'm going to go ahead and leave the 3 out and find cosine 30 and sine 30. If I look, cosine 30 is square root of 3 over 2. And I would leave the minus sign there, right? And then sine 30 is 1/2. And then there is an I for that second value. Then I would distribute the 3, so I would get 3 square roots of 3 over 2 minus 3 over 2i. This would be standard form for that complex number. Okay, now we're going to do products and quotients of complex numbers. And so if you have two complex numbers, okay, z1 and z2, they're both, if you look, in trigonometric form, then it works out that if I want to multiply them together, I take the r's and multiply them together, I add the angles and plug those in, and then if it asks for it in trig form, I'm done. If it asks for it in standard form, I'd actually have to work it out. Keep in mind, if we were in standard form and we wanted to multiply them together, then that's simply a matter of foiling. Okay. When I'm doing the quotient, I divide the r's and then I subtract the angles. Okay, and so this pattern here, this number 1 and number 2, that's pretty easy pattern to remember, in my opinion. If we were trying to divide two things that were in standard form, then we would have to multiply by the conjugate of the bottom. And it is going to ask us to do that in the homework, but right now we're going to focus on doing it with trig form. So this first example on this slide, find the product, express your answer in trig form and standard form. So z1 we have here, z2 we have here. We're going to fill it into the right side of this. So the product, z1 times z2, is our r's multiplied together, so 7 times 2. And in parentheses, we would put cosine of our angles added together. And plus I sine our angles added together. Okay, we would simplify that. 7 times 2 is 14. 25 plus 30 is 155. Okay, and so this is the trig form of that. If I want the standard form, then I'm simply, because this is not on the unit circle, I would simply be doing 14 cosine 155. Make sure you switch to degree mode. 14 cosine 155. So that's negative 12.69. And then 14 times sine of 155. So that is plus 5.92i. Okay, so I just typed that into my calculator and I got the standard form. Now let's find the quotient on this next one. So I'm finding the quotient of z1 over z2. That equals our r's. Okay, over each other, 2 over 3, and then our cosine of 30 degrees minus 60 degrees plus I times sine of 30 degrees minus 60 degrees. Now, this time, if we simplify it, well, I'm not really ready to say that yet. If we simplify it, we can't simplify 2/3, that's just a fraction. 30 minus 60 gives us negative 30 degrees. And again, gives us negative 30 degrees. This would be our trig form answer. It asks us to also put it in standard form, and so to put this in standard form, we would actually want to look at the unit circle because 30 degrees is on the unit circle. So the first example, we didn't have unit circle values, so we used the calculator. This one we do have unit circle values, so we're going to use our unit circle. The cosine of negative 30 would be square root of 3 over 2. Okay, so I'm going to distribute the 2/3 after I figure out these values. And then the sine of negative 30 will be negative 1/2. Okay, and it has that I next to it. So I just looked at my unit circle to find that. And then if I distribute 2/3 times the square root of 3 over 2, my 2's cancel, I get square root of 3 over 3. If I distribute 2/3 times negative 1/2, I get minus, the 2's cancel, and I get 1/3 I. So in standard form, this would be my answer. Okay, now we are to the special name, de Moivre's theorem. De Moivre's theorem helps us find powers of complex numbers. So if you have a complex number in standard form, like, I don't know, 3 plus 4i, if they ask you to, square that, that's not so bad. You write the parentheses twice, you FOIL, you're done. Or if they ask you to find it to the third power, okay, you write the parentheses 3 times, and then you FOIL once, and then you have to actually do distributive property on the next one. What if they ask you for the fourth power? And so on and so on. Well, this theorem basically is going to give us a way of doing that that's so much faster. Okay, if this is our complex number here, all we do is we say, okay, we're trying to do z to the n, so it's that complex number to the nth power, and so that means I simply take r and put it to the nth power and then multiply my angles by n. Okay, so the thing with this though is you do have to start off by putting this in trig form before you start. I don't really know what I was just talking about on the video. I paused it for a while, and so we're just gonna do this problem now. So we have to get this in trig form to start off. So this is like 1 plus 1i. And so if we think about where that point is right here, okay, then that tells us, hey, the theta should be pi over 4, and it tells us that our magnitude should be, or our modulus, or absolute value of it, should be 1 squared plus 1 squared, which is the square root of 2. And so we can write z as the square root of 2 times cosine pi over 4 plus I sine pi over 4. And now we can fill into this formula. So right here is what I'm going to be doing. R to the n, so we're doing the 5th power. So z to the 5th power is going to be the square root of 2 to the 5th power times cosine. When I get to my angle, I'm going to multiply my angle by n, and n is 5 because it's the power I'm raising it to. So this is going to be 5 times pi over 4 plus I sine 5 times pi over 4. Let's simplify this sum. It says to write our answer in standard form, which means we're going to be doing some distributing. The square root of 2 to the 5th is going to be, well, you'd have square root of 2 times square root of 2, and you'd keep going, right, 5 times. So these two become 2, these two become 2, but I have 1 left over to be the square root of 2. So if I simplify that, that's 4 square roots of 2. And then inside I have cosine of 5 pi over 4 plus I sine of 5 pi over 4. And then I need to look at the unit circle, figure out what cosine of 5 pi over 4 is. That's in the third quadrant. So the cosine should be negative square root of 2 over 2. And it's in the third quadrant, so the next one will also be negative and have an I. And then we distribute 4 square root of 2 into our parentheses. So this is kind of a tricky simplification, but the square root of 2 times the square root of 2 is 2. Okay, we know it's going to be negative, so this together is 2. 4 over 2 is going to cancel out and become 2, so this should be 4, because I did this. Okay, so this cancels with this and makes 2. Square root of 2 times square root of 2 is 2, so 2 times 2 is 4. Okay, and then the same exact thing should happen again, giving us minus 4i. So in standard form, this is negative 4 minus 4i. Who would have thought? So this is going to be the end of the first video.